Okay, so thanks for coming back. So I'm discussing I'll continue with the discussion of the decomposition theorem. Basically, we stated the theorem in words last time, but just let me write this down anyway. So this is yesterday. We introduced a way of constructing interesting perverse sheaves on any variety Y by considering some locally closed subset U. So we can start with U, which is a locally closed subset inside Y, where the first map is the open immersion and the second map is the closed embedding. So for convenience, we can always shrink our U by assuming that, for example, U is smooth. And then a typical way of constructing interesting perverse sheaves on Y are through, you start with this U, and you start with a local system. So you start with a local system on U, or more precisely, a pi1 representation. And then you do intermediate extensions through these two steps. You first do the intermediate extension. You get a perverse sheaf on Z, and then you extend by 0 by applying the I lower star. So yeah, this would be the I lower star, the intermediate extension shriek star of L, and you shift it correctly. I would just, for notational convenience, I would just use the du to denote the dimension of U. So this is to first make it a perverse sheaf on U, and then you do extensions. So, okay, so here, so every time you see this notation, the Z will mean the support of this perverse sheaf, because this is the second functor is basically extension by 0. So this object is supported on Z, and this L will be a local system. So, okay, so with this construction, so this will be a perverse sheaf on Y, and this is actually a very general construction. So we say that a few definition. We see that IC, Z, and L is simple if L is simple. So L is a reducible local system. So previously, if we only know how to define the reducibility of simple objects for local systems, then we know how to talk about a simple perverse sheaf. And then semi-simple perverse sheaves are just a direct sum. So these objects certainly already appeared in Olivier's lecture in the morning. So semi-simple perverse sheaves are, you just take them and take the possible direct sum. So are direct sums of simple perverse sheaves. But unlike the case of the local system, so a semi-simple perverse sheaf actually can have different supports. For example, if we consider, a plan. Oh, sorry. So this is because I try to push hard to make it more visible. So this is C2, and you consider x-axis, and you have an origin, which I denoted by P. Then a semi-simple perverse sheaf can be of the form, for example, the constant sheaf everywhere shifted by 2. So this is this is full support and supported on entire C2, and you can have a constant sheaf on X, but with a different shift. And then you can direct sum with a skyscraper sheaf at this P without any shift. So this is, of course, a semi-simple perverse sheaf. And okay, so last time we introduced this category of perverse sheaves by a pretty complicated support property. But actually, the definition is more complicated, but the property is much better. So this is at the heart in the derived category of constructible sheaf. So this is an abelian category But comparing to the standard abelian category of constructible sheaf, this is better. So this is actually, which is Athenian and Noetherian. In other words, every perverse sheaf can be thought of as an iterated extension of simple objects, and the simple objects are exactly the ones over there. So Athenian and Noetherian, and with simple objects defined as above. So in other words, if you care about, so essentially, you just use your most obvious ways of defining perverse sheaves, and they essentially gives you everything. You don't lose information. And then the decomposition theorem basically is just to, so this is actually the version for a morphism with singular fibers. So last time we saw Delign's decomposition theorem, which says that if you consider a smooth map, then the push-forward complex can be split into simple local systems, irreducible local systems. And this is the same statement, but the only thing is that you have to replace the irreducible local system by simple perverse sheaves. So let me just say it, x, let's consider x to y, f is proper. So for convenience, let's assume that x is smooth. Then let me just write down the decomposition theorem, which tells you how to think about this push forward of the constant sheaf, which is the relative cohomology of this morphism. So this is, I just write this in 2 lines. The first is the decomposition theorem. So here the DT stands for decomposition theorem, not Donaldson-Thomas. The first thing, it tells you that you can split as in the Delign's decomposition theorem, but you have to replace the cohomological functor by the perverse cohomological functor with respect to the perverse T structure. So the perverse, you take the perverse cohomology of this complex shifted by the cohomological grading, and of course globally you have to shift it by some uniform constant which only depends on the morphism. So I'm not giving you a precise formula here because so you just there's a unique constant so that the restriction of this one to the smooth locus recovering, which recovers the Delign's decomposition theorem for the smooth map. And then the shift is basically coming from because of when we consider perverse T structures, you always have some funny shift, and this will be absorbed by this constant. Okay, so the statement itself is very nice, but still it's not very explicit for doing calculation because it's because the perverse T structure is complicated. It's not very easy to calculate what this guy is. But the second statement is more helpful. It's the semi-simplicity. Which tells us that every summand here is semi-simple. So further, you can decompose the entire object in terms of the building blocks of the form simple objects. As I defined above, I, C, Z, some local system, some shift. So this direct sum is running through the support, local system, and the shift. Okay, so in other words, the push forward will be decomposed into just these guys. Okay, so this seems to be very helpful already, because but still, in general, it's very, well, these are called simple objects, but in general, to decide all of them, it is not a simple task. And I think later, I think Camila will talk about certain examples where how you can calculate this decomposition theorem explicitly. But OK, so now given, since I mentioned earlier, one of the tasks for this lecture series is to give some idea of how to controlling the support. So let me first define it. So the support of F is defined to be all irreducible Z that showed up above. In other words, we consider all subvarieties which served as a support in the decomposition theorem of F, and this is certainly as an invariant associated with the morphism F. And the goal and the hope is to, of course, to calculate these things as explicit as possible. So calculate the support Z. And of course, if possible, you would also like to calculate the local systems and the shift. And as I said, in general, this is mission possible because, I mean, it's just too hard. So now the second part of the talk I would discuss. Let's start with the support, and let me start with explaining why this matters actually. Why controlling the support in some sense is sort of the most important thing. So okay, let's first see some immediate consequence of the decomposition theorem. So let's assume we know this theorem, and then what we can obtain for a morphism. So let's come back to the picture we started from the lecture 1. Let's assume we have a proper morphism, and assume if we restrict to some Zariski open subset of Y, this is smooth. Okay, just throw out all the singular fibers and focus on the smooth part of the morphism. And then, okay, so then Delign's theorem tells us that if we consider just the decomposition theorem for the smooth part, we know exactly what happened. So this splits into local systems, Ri, Fu star Q, Xu, shifted by, sorry, this is shifted by minus I. So this is the Delign by the result of Delign. Okay, so if we forget about all the singular fibers, then only these local systems will show up. So then immediately from the existence of the decomposition for general map, we already know that. So this immediately will imply that, okay, what if we consider the push forward of Qx over the global of the global space? Okay, so we know that if we restrict this, so first of all, we know this can be split into simple objects on the one hand. On the other hand, if you restrict yourself to U, then you know that these are the local systems that will definitely show up. So combining this, you obtain that first, there are a large chunk of it which will be given by the intermediate extensions of these local systems. So first of all, these will certainly show up. Let me just write them down. So IC, we support the entire base, and Ri Fu star Qxu. Then, in order to make the shift correctly, I have to first shift this by I. Then, because when you do intermediate extension, there will be some shift absorbed here. So, assume I'm doing things correctly. There's a dimension y here. Okay, so this sum certainly will show up. But actually, there might be more. So there may be some extra. Is this visible by people on this side? Maybe I write it here. So there will be some extra component which we may not understand very well. Okay, so we know that this will certainly be the form of the decomposition theorem, no matter what the singular fibers look like. So the thing we know is that this F has supports. So the F will also be a direct sum of the IC of Z, ICZL with some shift. And then we can talk about the supports that showed up in F. And by this consideration, we know obviously that F has supports in the complement of the open locus. So okay, so this comes for free. If we know the decomposition theorem and the Lin theorem, we know that first you can write the decomposition theorem in terms of this form with a summand which, so far as mysterious, will be contributed by the complement of the locus we understand well. Okay, so there is an ideal situation, an ideal situation. So in the first lecture, we introduced a list of examples which all satisfy the phenomenon that, for certain fibrations, there might be very complicated singular fibers, but certain good properties carried by the smooth fibers are not destroyed by the singular fibers. But this might be a way to state that phenomenon precisely. So an ideal situation is so-called a full support case. This means if there is a method, so we can decide that the support of your morphism is only y. So that the entire base is the only support that showed up. This will immediately tells you that F will be 0. Right? And so in particular, this gives a full calculation of the decomposition theorem. And in particular, the smooth part decides everything, at least in the level of relative cohomology. So in particular, this is a mathematical precise way of saying that the boundary does not destroy things, which I mentioned a few times in the first lecture. Does not matter. Okay, so, well, of course, this is a very ideal situation. And the question is how to prove such a thing. There are, if you look at the statement here, then the naive or direct approach it's just to compare. So okay, so the decomposition theorem has already simplified the story a little. So we know we have such this F in any case will be a direct sum component. So in order to show this is 0, it suffices to check that it suffices to check for any closed point y which lies in the complement of U, the stock is 0. Yes, it's a point-wise statement. In other words, so this is actually a dimension count statement. So you have, so for any y in the base, you evaluate the left-hand side. Well, so then the left-hand side is just the total cohomology of the corresponding fiber. You just evaluate this, you consider stock over the point. And then what's the right-hand side? So the right-hand side is, well, you have this IC local system with shift, and then you evaluate, you restrict these over the stock over y. And then, so both sides actually are graded vector spaces. So these are, both sides are in the K0 of vector spaces. Okay, so if you know that, so the left-hand side is determined by the cohomology of a fiber, so determined by closed fibers. And the right-hand side, since they are given by intermediate extensions of some local system, so the right-hand side, in principle, only depends on U, on the smooth part. Okay, so if you are able to calculate this vector space, and compare the dimension, so if they have the same dimension, then certainly you would have that f is equal to 0. If they don't have the certain dimension, then f is not equal to 0. It's a dimension. It's a dimension calculation business. So this is the first or direct way of verifying whether this morphism f has full support. And this certainly works in certain examples, but in general, as you can imagine, this is not very effective. So the reason is because one of the motivations of using the decomposition theorem is that you hope to use the smooth fibers or the nicer fibers to control the bad fibers. But if you want to prove things this way, although this greatly simplified the statement. So originally you would consider the push-forward complex, which is object in derived category. This reduced the checking the full support property to a calculation only on vector spaces. But still, this requires knowing the information of every closed fiber. So it's too much things. There's too many things to request. Yes. Oh.
So
yeah.
I didn't quite understand when you said that the right-hand side depends on you, because why is in the complement?
So yes. So okay. So the right-hand side is completely determined by the data of the local system. I just erased the local system given by this morphism. Because after you know this, then you do intermediate extension with just a formal 6 operations, and you extend this to the entire y, and then you evaluated y. So the only input is some data here. And then all the rest of the things are all involved in this intermediate extension, which is given by abstract 6 functors.
Okay, so to compute the stock at y is there's some abstract way to do it.
There is actually a very precise way of doing, a very concrete way of doing this by delaying. Basically, you take a Whitney stratification. You start with some local system, the open part that you started with, and then you just consider normal push forward, and you do the truncation, the normal push forward truncation, and so on, along this stratification. So, I mean, a priori, this is computable, but of course, in general, I mean, in practice, this is very complicated. But in principle, it's determined totally by you. Yeah. But most of the time, actually, it's more challenging to handle the left-hand side. Because if for a certain morphism, then it definitely can happen that the singular fibers are very complicated. And in order to calculate the left-hand side, you have to know the cohomology of every closed fiber, including the worst ones. And it's going to be very hard. Yeah. So remark. So most of the time, this approach, this is not very effective, since it requires knowing the singular cohomology of every fiber, even the bad fibers. So in particular, so in order to use the decomposition theorem for explicit calculations, so we need some other method beyond this one to verify, or there is at least one should have some other method to rule out the possibility of the appearance of certain supports. Okay, so let me start with the first attack, which is called the Gorensky-McPherson inequality. So if there's one sentence to illustrate, to describe this, basically the takeaway is that, so this kind of equality tells us that a support, if Z is a support of some morphism, then the support cannot be too small comparing to the dimension of the fibers. So in other words, if in real situations, if you hope to rule for given morphism, if you hope to rule out the possibility of having a very small dimension support, then you may consider the techniques along this path. Okay, so let me be precise, stating the theorem. So the name, I learned this name from Engo's paper, who attribute this to Gorensky-McPherson, but the reference is Engo's fundamental lemma paper. In which he called this the Gorensky-McPherson inequality. Okay, so the statement is the following. So we consider the situation as before. We consider from the morphism from X to Y. And for convenience, let's assume both X, Y are smooth. And there is actually a more generalized version, but let me stick to the smooth words for convenience. So X, Y are smooth, and the morphisms, of, the fibers, of course, can be very, very complicated. And let's assume the fibers have dimension D. So you consider a morphism whose closed fibers have dimension D, but could be very singular. So the theorem consists of two parts. The first part says precisely that the support cannot be too small. So the first part, if any Z is a support of this morphism, then the codimension of Z is bounded above by the fiber dimension. Okay, so this is the first statement. So if you know what's the dimension of the, so in particular, this is helpful when you consider a morphism whose base have much larger dimension than the fibers. Because then you know that for all these subvarieties whose codimension, the base is greater than the dimension of a fiber, then these certainly won't be a support. And the second part tells you that even this is achieved, there's still a good way to control it. So if the inequality in A is an equality, if there is a support which has codimension D, then for some Z, then this Z, this support, can be detected by a constructive sheaf, which is R 2 times dimension, which is the top degree cohomology of the fibers. So we consider that there's nothing perverse here. We just consider that the relative H2D, the top degree cohomology of the fibers. This is a constructible sheaf, And the statement says that if there is a support which is of codimension D, then this support is detected by this constructible sheaf. So let me be more precise. Okay, so if Z is a support, then there exists V inside Y, which is open, and V intersect with Z is non-empty, such that and L is a local system on V, such that this top degree cohomology sheaf, if you restrict this over this V, you will see a local system. You'll see this local system as a direct sum component, and there might be some other things. Okay, in other words, if you look at this top degree cohomology sheaf, and you realize that, okay, so this is for example, this is like a constant sheaf or some sheaf supported everywhere on Y, then certainly there won't be any direct sum component supported on Z. Then you know that this equality will never be achieved. Okay, this seems to be a technical condition, but I will give you very precise examples how this can be used. So at first glance, actually, you probably think that the A is the more useful one because it rules out the possibility of having small supports. But in most of the time, actually, B is the very useful property. Okay, any questions? Yeah.
Is it possible that the support Z appears for other cohomology factors, like Ri of f over star to x?
Is it possible? You ask whether, not considering this cohomology, but other sheaves, or?
Yeah, to replace 2D by I, is it possible for support Z to appear?
No, the claim is that if Z is a support, it has to contribute this 2D pi f lower star. Of course, it can certainly contribute other cohomology, but this is the minimal. So if you don't see it here, then it won't appear at all.
So it could be 2D plus 1 plus 2, but not minus 1.
No, 2D, I mean, because fiber has dimension D, so if you go beyond 2D, there's nothing. So 2D is the top degree cohomology of the fibers because of this.
Another question.
Yeah.
Do you require more information about the fibers, like connectedness?
Yeah, right. So, okay, so of course you can, so here let's assume that everything's irreducible, but so let's assume X, Y smooth and reducible. Otherwise you consider different components, but for a smooth fiber, it doesn't matter. Oh, sorry, for a closed fiber, it doesn't matter. For example, a finite morphism, certainly this applies. A finite morphism, a closed fiber could be a number of points. It's not connected, this applies. And I'll give a proof, actually. So this theorem is not, the idea of the proof of the theorem underlies the entire proof of the Ngo support theorem, but of course, the proof, because in this setting, the proof is not very complicated. I hope to present the entire proof. And you will see how every condition is used. Okay, so since I want to use this blackboard, now I want to erase this theorem. If there's
L is on B.
L. Okay, so yeah, you know what I mean. So this is Z. Yeah, this is a Z intersect with V, maybe. Yeah. Okay, so although this is a long theorem, but it's two pieces of information. First, a codimension of support will not be larger than the relative dimension. Second, if the inequality is equality, then it's detected by top degree cohomology of the fibers. So now I'm erasing the statement, but I'm giving a proof. So the proof actually is that the proof goes by comparing two different T structures, but it is elementary in some sense. So proof. Let's start with the part A. So let's assume that the Z is a support. Sorry. So then we can define an invariant associated with Z, which is the index set of Z. Okay, so this is defined to be the collection of all I. You consider all possible i's such that the i's perverse cohomology of the decomposition theorem contains a simple object with support Z. So the index set of Z is, of course, is a subset of the integers. So because if Z is a support, then Z should certainly serve as a support of at least one of these perverse cohomology, and we just remember them, keep track of them. So okay, so this is just a subset of all integers. But the geometric input here is that the Verdier duality, saying that the push-forward complex, the Verdier duality tells us that the push-forward complex is self-dual up to a shift. So this in particular tells you that this invariant satisfies symmetry. So this immediately tells, as a formal consequence, this tells you that the index set of Z is symmetric with respect to the dimension of X. So in other words, this says that if dx minus I lies in this index set, the dx plus I will also be lying in there. This is by duality consideration. Okay, so in particular, can pick the m, some integer which lies in this index set, but also it's at least as large as the dimension of X. So we can pick such an integer by the duality. Okay, the claim is that this more or less does the job. Oh, sorry. This more or less completes the proof. As long as you can pick an m greater than dx, then you win. So in particular, just spell this out. This means, sorry. So this means that if you consider the m's perverse cohomology of the push-forward complex, it's not 0. And if we spell this out, writing this down using plain language, this means that there exists open U inside Z L local system on U since we know that this is semi-simple, so it has to be of this form, such that if you focus on some open subset of Z, then it has to be, so this perverse sheaf has to be of the form. shifted of the local system by z, and then since this appeared in perverse m, so you will need another shift by negative m. So this is a direct sum component, a direct sum factor of the push forward of qx restricting over this u. Yes, I'm just saying this is just a consequence of the semi-simplicity of the decomposition theorem. Okay, so I mean, what's this object looks like? So this object is L, a local system shifted by dimension of z minus m. So this, in particular, this means if you consider the push forward complex, that it will have a cohomology which supports in degree m minus dz. So if you consider this is the standard cohomology sheaf, m minus dz, this is definitely non-zero. Yes, because if you restrict this to u, you will see this as a direct sum component. Certainly, this is non-zero. Sorry, it looks technical, but I'm almost finishing it. So, okay, then so from this we already win because on the other hand, so the dimension of the fibers is equal to z, is equal to d, the constant we start with. So we know from this, and the base change, so this push forward complex, as a complex, this is concentrated in degree 0 to 2d. Well, this is related to Lucien's question. So you won't have anything going beyond 2d, which is relative dimension. Okay, then what it means? It means that so you have a non-zero so you will have a non-zero cohomology sheaf in this degree, but you won't have a non-zero cohomology sheaf beyond this degree. This tells you that m minus dz is bounded by 2d, and that this is exactly the bound of A, the part A of the property. So this tells you that m minus dz, which is the bound coming from here, is bounded above by 2d. But also we choose this m to be at least the dimension of x. So this is smaller than dimension of x minus dz. If you look at both sides of inequality, this tells you that dz cannot be too small, right? So dx, 2d, they are just invariants associated with the map. But just by comparing this inequality, this tells you immediately that dz has a lower bound. And then you just write this down. You realize that the bound exactly is the bound I wrote at the beginning. The codimension of z is cannot be too small. Oh, sorry, this cannot be too big. Okay, so this completes the proof of A. So the proof involves a lot of inequalities, but just, I mean, in short, this only, we use two things. One is that the index set, this index set has a center. It's symmetric with respect to some constant, and this is a consequence of the Verdier duality. And the second property is that since you have the relative dimension bound, it tells you the push-forward complex can only be concentrated in a fixed degree. So the degrees that this push-forward complex is concentrated at is the upper bound. Combining both bounds will already give you this estimate of the support. Okay, so this is the part A, and part B is actually easier. So yeah, so. So I leave this as the exercise. But actually, let me just say, let me say in words why it's true. So because if the inequality in part A is equality, this tells you that both inequality have to be equality. So in other words, so this L, this sheaf, L shifted by dz minus m, will certainly contribute to the top degree cohomology 2D here because of this inequality. And then you write down what exactly this means, then it will be the statement B. Just write down the definition, just write down precisely when inequality in, let's give it a name, star, are achieved. And this, you just write down, you don't need to do anything non-trivial, just write down when this is achieved, and this will precisely statement B. Okay. I have 13 minutes, right? 14, oh, okay. Okay, so, yeah, this is the, so this bond is already an interesting one. I will give you examples, maybe either in the last 5 minutes or next time, that actually this has very powerful consequences. But for now, let's get to the case of abelian fibrations. So in particular, I will explain. So this is the general bond one can obtain, and certainly you can find examples where the inequality is sharp. So for relative dimension, if you have a morphism of relative dimension D, then there are supports of codimension D. So in some sense, you cannot improve this further. But actually, when in the case of abelian fibrations, so there are many cases where actually you can improve this inequality and get better ones. So this is the main result of Ngo for the support theorem. So the reference is Ngo chapter 7, Ngo's fundamental paper chapter 7. And there is also a slight more generalization of this for any, which basically parallel to this, but just generalizing the statement from the constant sheaf to the IC, and the formulation of it can be found in the joint work with David Schmolik. The paper is called the cohomological kind, starting with cohomological kind dependence. And in chapter 1, section 1. So if you are comfortable with the Gorensky-McPherson inequality, then the statement, at least it should be easy to absorb. So the reason is that these two statements are of similar flavor, but here, because of the abelian structure, you can squeeze the bond of the previously in the Gorensky-McPherson inequality, the bond is given by the relative dimension. But when there are abelian fibrations, we can improve this bond a little. So describe the setup. Let me make a definition, and then state the main theorem. I will prove that. I'll give a full proof of the May theorem next time. So the definition is weak abelian fibration. Following and go. So a weak abelian fibration is a triple M, B, and P. So M and B can be viewed as the X and Y, the morphism between them before. So let's call this a weak abelian fibration of relative dimension D. If, first of all, you have a morphism F from M to B, so you can just imagine this is the morphism from X to Y as before. This is proper with M and B smooth. So I said this condition can be weakened. See, for example, the paper with Davish. And fiber, so you have a morphism which is proper with whose fiber dimension is D. So this is the same assumption as the Gorensky-McPherson inequality. And the second condition is more, it concerns this P. So you need a little more symmetry for the fibers. So the P over B, so this is a smooth group scheme. With connected fibers of dimension D. And these are two separate data, but the key point is that this P acts on M. So this is a relative action over the base B, and this with affine stabilizers. This is a smooth, commutative. You will never, so this is essentially about abelian varieties in GM and GA, commutative group scheme. So this requires that the action, the stabilizer, cannot be of like abelian varieties. Okay, let me state the May theorem. So if you read Ngo's paper, you find that actually in the definition there's one extra assumption, which is that, let's put a star here, so which is about the group scheme. So the Tate module associate with the group scheme P is polarizable. So this is essentially a linear algebra data about the group scheme. And nowadays, for most examples, this condition can be removed. For example, as long as the M is quasi-projective, then this condition is satisfied automatically. So this is not, in most of the cases, this is not something we have to worry about. So that's the reason I put a star here. And I think probably Camila will discuss more about it in her session. Okay, so assume you have a weak abelian fibration, which I will give. This is, let me say, always okay, almost always okay in practice. So you can ignore this for the moment. So the theorem, let me state it and finish. Okay, sorry. Before stating theorem, let me introduce one more piece of definition. So the purpose is to squeeze the codimension bound of the support for this morphism F using the group scheme P. So to do this, I need another definition, which is the delta function. So let's consider the group scheme as before, and then for for any, so this is a commutative group scheme. Then for any closed point on B, you know that the PB is a commutative group over a point, over a field, and it satisfies the Chevrolet decomposition or Chevrolet de Visage. It can be written as an extension of the abelian variety and an affine part, the affine group scheme. Yeah, so this is R. Here RB is affine, and AB is abelian variety. And we define for any Z which lies in B irreducible, we can define the delta function of Z to be the dimension of this affine part. So we can ignore this abelian part by only remembering the affine part of the fibers for B in this Z general. Okay, so if you consider Z, then for every fiber you have a number which is the dimension of RB, and this is a constructible function, and it takes the same value on the general point of Z, and you just define this to be the delta value of the Z. Okay, so this is the delta value. And Engels' support theorem, as he stated in his paper in chapter 7, is exactly Gorensky-McPherson equality, but you just replace the relative dimension D by this delta. And then all the other statements are identical. So let me finish writing down the statement and conclude today's lecture. Now today this part is the most technical part, and then after that, I will move back to the concrete applications, and you will see how powerful it is. So theorem, this is what is called an Engels support theorem. The two parts. If you start with a weak abelian fibration, as above, then for any C which is a support of the F which goes from M to P, we have the codimension of Z is bounded above by, well, so the relative dimension of course is PB, but we can ignore this part. It's only controlled by the affine part, so delta Z. So first, we know that every support cannot be too small, and actually the upper bound is given by this delta. And the second, part is that if the inequality is indeed an equality, then the Z can be detected by our top degree cohomology of Q. So I just wrote things this way because I stated a precise version in the Gorensky-McPherson setting, but it's the same thing. Okay, so I think I have maybe 1 or 2 minutes. Okay. Let me say in words why. So next time, of course, I will explain details and real applications how this can be applied. But first of all, why this is helpful, because if you look at the literatures in classical algebraic geometry, there are many, many inequalities of the other direction. So for example, if you have a smooth family of curves, and assume that corresponding modular space, the relative modular space, like relative comparative Jacobian, if the total space is smooth, then usually for any subvariety, you actually get a codimension lower bound. So this appeared a lot in classical algebraic geometry. But the Ngo support theorem tells you that actually you have an upper bound. So in the concrete situation, if you are able to compare this upper bound from this theorem and some lower bound that you already know, then basically in many situations you can use a combination of these two ingredients to rule out the possibility of smaller supports. And at the first glance, this seems to be not very convincible, but actually it turned out to be very powerful. This is thing number one. Number two is that, okay, so there are many situations where you will see that this inequality is indeed an equality. However, for example, if you know that in many cases, you know that morphism from M to B has complicated fibers, but the fibers are integral. So in this case, you know this will be a constant sheaf. It's a trivial local system, because this calculates the fiber-wise top degree homology. So if every fiber is irreducible, then you don't have jump for this sheaf at the smaller locus. So in particular, this B can be checked automatically in these settings, because if the equality is achieved, there will be a smaller support detected by this. But if this you already know does not jump anywhere, you can know that this is not happen. So you can know that this equality even will not happen. Okay, so as I said, I will talk about more details, but let me stop here.